string wrapped around
No, he said he's
3 loops. Yeah, for real.
Hey, how do you solve? What do you mean study? You solve it? Study. Yeah.
Denny, you still have a crush on somebody? Huh? I asked if you still have a crush on somebody.
No comment.
Okay.
I plead the fifth.
Which ones did you miss? Alright. I missed the elevator one. Yeah, I missed that one.
Have a good weekend.
I'll see you next week. Friday.
Mr. Dunn, I made you. Rebecca. I made you.
Why are my arms so short? Why is my neck so long?
I don't know, it's based off of your image.
Which image?
An image like this.
I mean, you can keep.
Townsend, don't be mad at me, I bring a donut.
I don't want a donut. I don't want a donut.
It's nothing, it's a trash. Oh, he actually deserves that, because he said he was gonna get a donut and step on it in front of me, so I appreciate that.
Mr. Reef already saved me one.
Oh, really?
Yeah. I just called him a minute ago.
No, I don't believe it.
Did I call Mr. Reef?
Yeah. Yeah, I did. But he didn't save a donut for you.
He did.
Truth.
Maybe you weren't watching him.
Now, do you like my gift? You do. I know. Goodbye, Mr. Townsend. Is a ball of energy today. Let me tell you. Are you serious? Why?
There's another way I can use this.
We didn't get last time. We didn't get last time. No, it wasn't in there.
I'm this one. And you would be like, you would be Charlie Penis. There you go.
The tree.
See, that's funny. Because it's not an animal.
Yo, we start
And it's
That's
ugly.
funny. Yeah, I get it.
Hey, do you have anything on the carpet?
So,
Boom! And then you die.
You meant
Well, it's because Dennis told him to move around.
Is Dennis having
Yeah.
to over that?
No, his Dennis told him to move around because it was like burning a hole in his mouth.
Wait till his dentist finds out about the COVID.
No, that's what she asked if he did. And he said yes.
It's like it doesn't count now.
He said yeah because my mom found one. That's what he told her.
That's just culture.
Why are we throwing that toward Dennis? What else are you gonna say? I mean, what are you gonna be like? No. I've seen a million dollars. Probably all had the same thing.
Alright guys, I think I got number 28 for most of you, but we have been a little disjointed with the short period on Wednesday. So you need to double check that 28 either has a grade on it or come turn it in, please. And then we've got one full class period that we're going to focus just on assignment 29.
You have no excuse.
And you'll have to remind me, but I'm pretty sure we've done the notes for 29 and that's it. Is that correct?
I don't, no, we didn't do notes.
We didn't do the notes for 29?
We have no everything.
Okay. Do you have the handout for 29?
I do.
I just got it.
Okay, does anybody need the handout for 29? Harper will get it for you.
What? I have it. Oh.
Does anybody need handout 29? Okay. Then let's go ahead and talk about what's different with 29. Sorry, I guess this is where we were a little bit behind with our 50-minute period. Okay, and this is the last part of polar. So 28, where we were finding area bounded by a single polar curve. This is basically the same skill, but we're going to have to try to think of some of these problems as addition and or, well, not and, or subtraction. Okay. So we are still going to be using the same old formula from 9.8, where the area of the polar curve is going to be found by doing 1/2 integrate alpha to beta r squared d theta. And I highlighted the angles because just like finding the correct angles in 9.8 was pretty much the only challenge. Granted, it's a hard challenge. But that's also the majority of what's challenging about these as well. So things to look for, where two polar curves intersect is often a point of interest. So points of intersection is something we're going to talk about. And then symmetry is usually optional, but using symmetry can simplify these questions. So what I mean by the symmetry is, like down here in a second, we are going to try to find all of this area. And so to make it just a touch easier, we will just find like this area and double it, basically, because we can see that that's half. Okay, so find the area of the region bounded by the polar curve 4 cosine theta and 2 sine theta. Okay, so again, just like 9.8, 9.9, part of the hardest questions are when we don't know what the graph looks like, it's not given to us, like this one is, and if it doesn't say use a calculator, we shouldn't just graphing in our calculator. We have to practice making these graphs so that we can see those things, and within making the graphs, we're discovering some of the angles and probably going to discover the angles we need. So I tried to push two things on you in 9.8 as far as graphing. You could plug in 0 for r, solve for theta, and then you would know all the places that hit the origin. I also pushed pretty hard on making a table, plotting points, and using those points to try to figure out what the graph looks like. So you can do that. Now, the more of these you graph, there are some overlap in that if you're paying attention, you might learn some shortcuts on how to solve or how to graph these. These two, I actually know what both of these look like. So if you know what r cosine theta looks like, it's a circle with diameter 1 centered around the x-axis. Cosine, x values on the unit circle focused on the x-axis. This 4 just makes the diameter 4 times bigger. So that's roughly what that one looks like. And r equals sine theta is the same idea. It would be a circle of diameter 1 centered around the y-axis. Sine has to do with y things. So if it's 2, it just changes the diameter to 2. Now again, you don't have to know that, but if you do know that, you can skip plotting a bunch of points to find this area. Okay, now I'm going to redraw my picture. I'm going to erase this picture and redraw my picture, and then I'll show you why in just a second. Okay, so the problem is, if this is the area we're trying to find, we're trying to find the common area region. Sometimes, and this is where it's a little challenging, but sometimes it's bounded by, I'm just going to refer to them as red and green. Is anybody here colorblind? Okay, I'm going to refer to them as red and green. Sometimes this is bounded by the green polar graph, and sometimes it's bounded by the red polar graph. So we're going to actually have to find two areas and add them together to get this. So notice here at the start, I don't want the area bounded by the red polar curve, because that would be getting all of this stuff. As theta gets bigger, I would be getting all of these sections, and I'm not interested in this area. So at first, I only want the area bounded by this green polar curve. Go to the green polar curve and stop. But there becomes a point right here where now I don't want to continue with the green polar curve, because if I do, it's going to keep going too far and it's going to give me all this area that I don't want. So once it gets to this intersection point, now I want to only travel to the red polar curve. Now, even though I tried to redo my picture here, you can see that's pretty bad. And the worse your picture is, the harder it is to see how to divide this up. But basically, we're going to just make two of these. So 1/2 integrate alpha to beta r squared d theta plus 1/2 integrate r squared d theta. And then I'm going to call this my green stuff, and this my red stuff. Adair, you still with us? Yep. Okay. Okay, so I've got to figure out what angles start this green area and end at this green area. So I think, since this is going directly to the right, this is probably 0 radians, but some of these are kind of tricky, especially if there's a number next to theta. So never assume that. Actually plug it in up here. 2 times the sine of 0 is 2 times 0. So that makes sense. This is at 0 for 0. So I want to start at 0 radians, and then I want to keep getting all of these angles until I get to this intersection point. And I need to figure out where that happens. So now if we have a calculator, we could graph each of these and we could ask our calculator to find the intersection. Without a calculator, I just need to set these two things equal to each other. If 4 cosine theta is equal to r and 2 sine theta is equal to r, then I can set this r stuff equal to this r stuff. Divide both sides by 2. And then sometimes this is going to be something I could do in my head. If I could think of some angle of cosine that I could divide in half, that would give me the sine of that angle. If I could just reason through that, that would be great. But I'm not going to be able to do that because we don't memorize that spot on the unit circle. So instead, what if we divide both sides by cosine? And instead of saying sine over cosine, let's call it tangent. And if I want to know that angle, the angle that has a tangent of 2, that's not a unit circle ratio. So we would have to be allowed a calculator at this point. Theta could be found by doing inverse tangent of 2. So if the tangent theta equals 2, then inverse tangent of 2 is what the angle would be equal to. Of course, truthfully though, if I really needed a calculator for this, then I guess I'd have a calculator for the whole thing, and I could have really done that with the graphing as well. But that happens at 1.07 radians. And notice, based on my picture, that's where I want to stop including the green area and start including the red area. Bless you. I guess I can also plug in these r's. This is 4 cosine theta, and this was 2 sine theta. Okay, and then the last thing is I need to figure out what angle do I want to stop at to stop collecting this red area. Again, it's a little harder to see here. I'm trying to emphasize it a little bit. But to me, it looks like the angles keep getting closer and closer and closer to going straight up, which I anticipate to probably be pi over 2. But in the pi over 2 direction, I need it to be 0 for that to be the case. So if I plug in pi over 2 into that polar curve, 4 times the cosine of pi over 2 is 4 times 0, which is 0. So pi over 2. So again, the challenges are still the same, but you need to see this and emphasize this in your notes. You've got to split that up. Sometimes we wanted our area to be trapped by this polar curve until I got to this intersection, and then I wanted it to be trapped by this polar curve. That's why I have to do it in 2 parts. This area plus that area gives me the area of the whole thing. And then if you just throw all that in your calculator, there's your answer. Okay, are you guys okay with how I said this plus this equals the whole thing? Okay, then the next one is similar, where we're going to have to take part of an area plus another part of an area, but this one we can at least use symmetry, and this one's graphed for us, so we wouldn't have to do any table necessarily. We don't have to spend a lot of time doing investigation. But if we try to find the common area this time, that's going to be all of this stuff. So what I'm going to do, and again, this is just a choice, but I'm going to say I'm not going to find the area, I'm not going to find my answer, I'm going to find half the area, and I'm only going to worry about half of this stuff. Now, don't just hope that you remember that. If you do that, make sure that you say half of the area, and then that way you remember to multiply by 2 at the end. Okay, but this is kind of the same idea. So I'm going to do blue and black this time. I know yours doesn't copy in color, but this was supposed to be in color. Thank you. So right here, oops, I only want the area to go to this. Yeah, I only want this area to go to the black polar curve, because if it was going to the blue polar curve, I'll draw it in and then erase it. If it was going to the blue polar curve, I would be getting all of this stuff. I'd be getting all of this area that I don't actually want. So the first little piece, I want area to be bounded by this black polar curve. So 1/2 integrate alpha to beta r squared d theta, where r is this guy. This is r equals 2. And then we just need to find the angle where that starts at and the angle where that ends at. So it looks like it starts at negative pi over 2 because it's going straight down, or 3 pi over 2. You could call it either one, I guess. I'll call it 3 pi over 2. So, I don't know. I mean, it's kind of a weird polar function. Somebody just came in. It's under this TV though, if it's still there. This equation is r equals 2. There's no theta in it. So regardless of what theta is, r is always 2. So that's just a circle. That's why it looks like a circle. So this I could call 3 pi over 2. And then this I could call 2 pi. Or you could do negative pi over 2 to 0. That should be okay also. But what I need you to, and again, this part's not so different than what you have done. But what I need you to realize is that at some point in here, this area that I'm trying to find is not trapped by this black polar curve. It's trapped by the blue polar curve. So at some point I have to say plus the area of the blue polar curve. So 1/2 integrate r squared, and then I need it from this angle to this angle. So when it goes straight to the right and when it's r is 0. So straight to the right, my guess would be this is probably where theta is 0, but again, sometimes it's tricky, especially if there's a number next to theta in the equation. So plug it in. Sine of 0 is 0. 2 minus 0 is 2. It's going 2 in the 0 radians direction. That sounds correct. So I'll go with 0. And then the angle gets bigger and bigger and bigger and bigger, and the bigger, looks like the angle is trying to go straight up. So I think this probably ends at pi over 2. But if I plug it in over here to double check, when theta is pi over 2, I get 2 minus 2, which is 0, which is exactly what it looks like on the graph, so pi over 2 makes sense. And then I throw all this in the calculator, and I don't get the right answer. Why does that not give me the right answer?
You need to multiply.
Right. Remember, I only did half. And if you want to do the whole thing, you can. It's just that you're going to have to be even more careful about the angles. Like, it's not that it's impossible or anything. It's just easier to do work with a couple angles than it is to work with all of those angles. So all of this in my calculator times 2, and then we can get our answer. About 7.7 square units of area.
Just use the area of the circle to get the first part.
I did. Yes, you could. I'm sorry. And then divided by 4.
Yeah.
It's the same thing, so sure. Okay, so again, same challenges as last unit. You're still going to get a little bit better at that, which is good. But what's unique here is you need to see how this is divided up. Some area was trapped by this. Some area was trapped by that. We got to take this area plus this area to find the area that they want us to find. Okay, so the first 2 examples have to do with adding area. And then the third example also will. There's only one example of subtracting. So here's the third one. So when it says r is -6 cosine theta, do you guys know which one of these is -6 cosine theta?
The black circle.
The black circle, okay. How could you figure out that it's this one if you weren't sure?
Because the graph of cosine is a circle. The polar graph of cosine is a circle.
Well, that's true, but let's say it was a different shape in a different equation. How could I know which one was which?
Just plug in one.
Yeah, just plug in something for theta and see which equation it lands on. So then you could be sure which one is which. Okay, this time we're trying to find the common area. So we're trying to figure out where they both have area, which to me looks like all of this. So you can go ahead and find all of that if you want to. Just like the last question though, I'm going to use symmetry and I'm going to find half the area and then I'm going to double it. And so I remember that. I'm not saying my answer or the area equals, I'm saying half the answer or half the area equals. This way I'll remember to multiply by 2 at the end. Okay, so do you see 2 sections of area that we need in this?
Yes.
Okay, the first section, let me just go ahead and write out the parts I know are going to be here. Okay, there are 2 parts. The first area, when I say the first, I mean the one that's, if we're just trying to think of like, as the angle gets bigger, probably starting at 0 and slowly increasing, is the first area trapped by the red polar curve or the blue polar curve?
Red.
Is the red. I only want it to go to the red. I don't want it to go to the blue, because if it goes all the way to the blue, it's getting all this area too. And then how long do I want to do this?
Until that intersection then?
Right, because if I stick with the red, you see how if you keep doing it too long, it starts getting this area that you don't want? So it's really to right here that I want to stop the red, and then I want to start the blue. So red, then blue. So here's the red R, -6 cosine theta. Here's the blue R, 2 minus 2 cosine theta, or 2 minus 2 cosine theta. And now if I can just figure out the angles when the red area starts and stops, and the blue area when it starts and stops, so I can update the angles, my work is done. All that's left would be making sure I put it in the calculator correctly. So for the red, since it's starting here, to me, my guess would be that it looks like it's trying to go straight up, so it's probably at pi over 2. So in the red polar curve, if I plug in pi over 2, I'm hoping that it's 0, because it starts off at 0 here. So -6 times cosine of pi over 2 is -6 times 0, which is 0. That's great news. That's what I expected. 0 in the pi over 2 direction. So this is pi over 2. Okay, we wanted to keep including the area until we get to this intersection. So how many radians is this when they're both at the same place at the same time?
You can set them equal to each other.
Okay. How does that help?
And you can solve for theta.
Having a stroke. Okay. So when there's 2 times where cosine's -1/2 in just one rotation. There's infinitely many times if you go around the circle enough. When is cosine -1/2? Pi over 6 is in quadrant 1, so cosine would be positive there. Okay, negative pi over 6, or you could call it 11 pi over 6. Wait, never mind.
Yeah.
Sorry, that would be sine.
5 pi over 6.
At 5 pi over 6, cosine's -√3/2. Cosine's the x values.
4 pi over 6.
I want the small values to the left. 5 pi over 4 is here. This is 2 pi over 3. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, which it reduces to 2 pi over 3. And then notice this picture, look where 2 pi over 3 is. Right here. Doesn't that look like 2 pi over 3 now? Doesn't that make sense? So 2 pi over 3. Now, I get to double dip on this one. That's where I want to stop collecting area from the red polar curve and where I want to start collecting area from the blue polar curve. So I get to use that here and here. Okay, and then I want to start collecting area. Man, I don't think my picture could get any messier here, but I want to start collecting blue area until I get to this. And what would you guess this angle to be? Probably pi, because it's straight to the left. But let's plug it in real quick. 2 minus 2 times the cosine of pi would be 2 minus 2 times negative 1, which is 2 plus 2, which is 4. Does it go 4 in the pi direction? Then that's what I wanted. That needs to be pi. Throw all that in the calculator. Don't forget to multiply by 2, because remember we did symmetry, so we only had to do half of this. Again, it may be not even harder to just do the whole thing. I'm not saying that it's easier, but sometimes it's easier, so I tend to do that. Double it, throw it in your calculator, and let it do the antiderivative stuff. 15.708. So once again, it's like finding area bounded by a polar curve, area bounded by a polar curve, and seeing that you need to add those together to get what you want. So there's 3 examples in a row where we had to add those areas. Now let me point out one thing to you real quick before we look at the last type of problem, which is subtraction. Even this picture given to me, once I started thinking about the area, notice that this perfectly done picture is perfect because computer did this. It's still kind of challenging sometimes to see to divide it into 2 parts. Sometimes it's bounded by the black polar curve, and then sometimes it's bounded by the blue polar curve. So even with a perfect graph that I can zoom in on, it's kind of hard to see to divide it into 2 parts. The question before that was a little bit easier, I think. But to find this area, and then I just did symmetry, so I really only worried about this area. This one was a little bit easier to see that sometimes it was bounded by this black polar curve, and sometimes it's bounded by this blue polar curve. But again, it's a lot easier because they did the graph for us. And then the question before that, remember I even redrew my picture, and it's still pretty tough to see sometimes that some comes from one and some comes from the other, that it needs to be divided into 2 pieces. I say all that to say when you need to make a graph, you need to be extra careful, try to make it to scale. Otherwise it's going to be very easy to miss little slivers of area like this. You're going to think it's all bounded by one polar curve. Okay, so the subtraction piece, this would be like if we wanted to know this area, what we could do is, notice here's alpha and beta. We could take this whole area, and I'm going to call this R2, radius 2. So I could integrate, or do 1/2 integrate alpha to beta R2 squared d theta, and that would give me all of this, and then I could come back and subtract how much of it is not supposed to be my answer. I'll call this small radius R1. So 1/2 integrate alpha to beta R1 squared d theta. Or we could just combine these into a single statement. They both have a half, they're both integrating from alpha to beta, they're both d theta, and we could combine these into a R2 squared minus an R1 squared. This looks a little bit cleaner. But basically, sometimes you need to use subtraction. You need to find the area of some bigger shape, and then come back and take away the area that's not part of the shape you want, and then that should leave behind how much area you do want. So we've got just one example of this on the next page. where we would have to do subtraction. There's no way to split it up with addition. Now they've graphed this one for us. So it's a little bit easier to see. But I'm going to use symmetry this time, and I'm going to just find this area and then double it. So half of my answer, half of the area is going to come from. Now notice, if you try to divide this into a couple segments, it doesn't make sense. Like, for one instant, it goes from the origin to this black polar curve, but soon after that, you don't want it to go to the black polar curve because it's like you don't want this area. Like, you need it to go over here because you need that area, but you don't want this area. So instead, let's start off with, let's just find this area. And since that's just a quarter circle, we could do a quarter of pi r squared, and r is 1. So 1/4 of pi r squared. And then come back and say, well, wait, let me subtract. This would be too much area. If I do the whole thing, I get all of this. I need to come back and subtract this stuff that's not supposed to be part of my answer. So minus this area is 1/2 integrate alpha to beta r squared d theta. And now I just need to figure out what angle did this start collecting area that I don't want, and what angle does it stop collecting area that I want. So this one's probably 0. So if I plug in 0 here, then I would get 1 minus the cosine of 0, which is 1 minus 1, which is 0. So I was correct. Start at 0, and then the angle gets bigger and bigger and bigger and bigger and bigger until it's trying to go straight up. So this angle's probably pi over 2, but plug it in to its equation and make sure that that gives you 1, because in the pi over 2 direction I think it's going up 1. So 1 minus 0 is 1, so pi over 2 is correct. So again, this is too much of an answer because it would be this whole quarter circle. So I just came back and subtract this little wedge that's not supposed to be there. And again, this is really only half the area because there's the same thing over there. So when I double this in my calculator, it gives me the answer. So you really just need to see how and why I'm trying to subtract there.
Should the pi there be squared
The pi?
with the area of the circle?
No, area of a circle is just pi r squared. Only the r squared. Okay, so let's have you try some of these, but skip number 1 for now. My B-Day classes didn't have the same issue with PSAT, so some of them had this finished yesterday, even though they didn't have to have it finished. But they said 1 and 10 were the two that they thought were the hardest. So it doesn't make sense for you to start with one of the two hardest. Come back to this one after you've done a couple others. Start with question 2. Try it, get an answer. If your work and your answer matches up with the answer key, keep going. And if not, please consider watching one of the class videos. I did record videos of all of these yesterday except for questions 7, 8, and 9, I think. So I would like to try to make videos of those in case that would help. But of course I also want you to try to get a chance to get there before we do that. So you've got about 12 minutes before lunch, so try to do maybe 2 of these would be good. If you could do question 2 and 3 before lunch, that would be great. I know we won't have time to discuss all of them question by question, but we've got just enough time to look at question 2 before lunch. So again, if you got the right answer, tune me out and just keep moving on with question 3 and 4. But if you're struggling on 2, you're going to have the same issues on some of the next questions, so you might as well try to clear it up right away. Okay, so again, each of these always come with an asterisk. Sometimes a graph's given to you, sometimes you have a calculator that you could just graph these two to see the graphs. All that makes this easier. Worst case is you make a table, plot all these points, you make a table, plot all these points, and then you discover what the graphs look like. Both of these are the shortcut that I had mentioned earlier though, so that's how I can do this so much quicker. So if you know what cosine theta looks like, 2 is just twice as big. If you know what sine theta looks like, 2 sine theta is just twice as big. Okay, so here's the area, and then I think this is again, I can kind of zoom in a little bit so it makes it a little easier to see why there has to be 2. At first, your area is trapped by this one, 2 sine theta, until you get to this point, and then you want the area bounded by that polar curve. There's 2 pieces there. And again, even though my picture is not that bad, and I'm able to zoom in to see it, it's hard to see that that's split into 2 pieces. But once you realize you've got to do something plus something, you are very close to being finished, because you know what the area formulas are. I can see I'm going to start with this one, so I'm going to make this the first R, and I'm going to finish with this one, so it's the second R. And then as soon as I find those angles where all that's happening, then I'm ready to throw this in the calculator. So right here with my green stuff, I would assume that this is probably theta equals 0. If I plug it in, I can confirm it. The red is ending here. The angles are trying to go straight up, so I would guess it's probably pi over 2. And when I check it, it works. So that one ends at pi over 2. But this intersection point, when it stops being this polar curve and starts being that polar curve, you've got to figure out where that happens. And so set the 2 equations equal to each other and solve, and you could either do this. I think you should be able to answer that, or I guess you could divide both sides by cosine and call this tangent. That's the same thing. Where is tangent 1, or where is sine and cosine the same thing? Pi over 4. So pi over 4 is when it's switched from being that part of the area to that part of the area. So that's what should give you 0.571. Okay, if you struggled with that question, is there anything you can ask here that will help you? Okay, then my only question before I get cut off here, did you see on your own that this got cut into 2 pieces? Okay. Okay, we'll worry about it after lunch.
Like the blonde tips fell off.
Yeah? You had enough of them?
Yeah.
I was realizing I was due for a haircut on that long weekend last weekend.
Oh yeah.
But I hadn't made an appointment, so I was like, well, I don't know when I'm going to do it then.
Yeah.
So I'm going to try to do it Friday afternoon.
Oh yeah, 'cause you're not on school next Friday either.
Huh?
You're not on school next Friday either.
Teachers do. We have,
Oh.
we have morning and parent teacher conferences. So I'll do it.
So yeah, like a half. That's good after.
But then we have to work late. We're still doing a 5-day week.
Yeah. That is. I didn't know I hear that. You don't know that?
Wise words from Mr. Dave.
I need to watch that clip. Oh, his son's looking at him. We're trying to compare him and Woods, but the age difference is too big, so you can't. Like last weekend we were at my house after Cecil's house, and they were talking about it. I don't want to step in, and I was like, their age once, like, for her birthday. And they said, absolutely not. Do not buy that.
I had to wash
Buy
it
something
first.
else.
That's a good idea.
Because
They're expensive.
his stench.
Well, and they're not having birthday on their son, so they're gonna graduate.
What?
They
Yes,
just-
he lives very close. Very close.
Should be put on.
Have you gone here at 50 school?
SAT?
Yeah. You took it.
Shit.
No, some took it.
What's yours?
You do the same thing. You do the same thing.
Yeah.
Where do you see it?
We had a little baseball.
Oh,
We had a
yeah.
little baseball.
Seems so hard. Use like.
All right, take a seat, please.
That eggshell is a lot.
Harper, that's you.
Let's see what locked on the mat section. Just better, bro.
How did it look like you could so
Okay, guys, what I'm going to suggest, which I think might be the best help for you, is, again, I recorded a lot of these questions as videos yesterday, but there's a couple that I didn't do, so I'd like to do those, and then that way you have access to help on all of them if you need it. So that is questions 7, 8, and 9. So if you, well, I'll leave it up to you. You can tune me out while I go over those questions on the board, or if you want to try them before I go over them, that's fine, but if you want to do that, please jump ahead to question 7 and then do 7, 8, 9 in order. But if you want to just pick up where you were at question 3, that's okay too, but I just would like you to have access to help on all of the questions before y'all leave. So I will be asking for this at the start of Monday's class, so please try to get, let's see. I don't know, there's only like roughly about 9 more questions, so I don't know if you can do that in the second half class, but if you don't, you should have very little homework. So let me give you a minute to do question 7, just in case you want to do that before I talk about it, and then I'm going to do 7, and then I'll give you a minute to do 8 before I go over it, and then the same with 9. And then I'll be happy to help with anything, but at least the others have videos, so if you had to resort to that, at least you have the backup. So I will set a 5-minute timer before I go over 7.
I'm going to go over question 7. So if you want to follow along, you can. And if you're not there or you haven't tried it yet, I will record it so you could watch it later if you needed to. Okay, so this one, we're supposed to find the area inside a polar curve and outside of a different polar curve. So no graph is given, so first minute or two should have been set aside to trying to graph these. Now, both of these are pretty easy for me to graph. R equals 1 is just a circle with the radius 1. No matter what theta is, R is 1. And then 2 cosine theta, again, you can always make a table, do enough points, plot the points until you can discover what the graph looks like. But again, if you know that cosine is centered around the x-axis like this, and it has a diameter of 1, so if you put a 2 in front, it just multiplies all those, doubles all those values, and it would have a diameter of 2. Then it looks like this. So we're trying to find the area inside of this one, but outside of that one. So you're trying to find that. Now, I think the first time I did this last year, I just found the area of this whole red circle and then tried to subtract this. The problem with that was, it's not that it's a problem, but it makes the question a little bit harder. If you do it that way, you have to come back and there's some stuff that you have to subtract away that's not really necessary here. So instead, what I could do is I could find the area of this entire red thing, but I'm only going to find from this angle to this angle, the 2 intersections. Because then it's like I'm doing this, and I'm only going to draw in just enough to where it's not too hard to see. So that's going to be too much, so I'm going to have to come back and subtract. But if you, again, I'm really only going to here, I'm not going past those angles, so that I don't have to come back and subtract. So the area of this guy is going to be 1/2 integrate 2 cosine theta squared d theta. And I want to start at this angle and end at that angle. So those intersections set, if r equals this and r equals that, you can set the 2 things equal to each other and solve. And then cosine is 1/2 at pi over 3. And down here at 5 pi over 3. Now, here is a general question for everybody, even if you don't think you need help with this. Why is it a bad idea to say pi over 3 to 5 pi over 3, even though cosine is 5 pi over 3 here? Right, it would be getting all of the area between those 2 angles, which is not what I'm interested in. So don't call it pi over 3, call it, or 5 pi over 3, call it negative pi over 3. That way, starting at negative pi over 3 to positive pi over 3 is getting those angles, which is where I'm actually interested in. Now again, that would get all of this red area, which is a little bit too much. In fact, it's this much too much. So we can come back and subtract the area that's bounded by this polar curve. So r squared is just 1 squared. And then it's going to be the same angles. I want to make sure that I take away, I subtract all of this stuff to that one. So negative pi over 3 to positive pi over 3. Now again, this is not the one and only way to do this. Most of these questions have many different paths, but of course you want to try to pick out the one that is easiest and most efficient to you. So that's what I would do with that one. Okay, I'm going to leave this up for a few minutes, and I'll give you a 5-minute head start if you would like to do question 8 before I go over question 8. If you want to test and see if you do the same thing that I do, this is your chance.
Take the back pass. But hand it to me when you're back, please. Okay, I'm gonna go over question 8 now. So one thing I haven't had you guys think about that I think would help is I know I've been pushing you to try to make your graph, you know, kind of zoomed in, a big graph, a fairly accurate graph. The better your graph looks, the easier it is to kind of figure out some of these angles you're supposed to be working with. But one thing I haven't really talked about is, like, when you're making your graph, you know, if you really want the picture to be as big as possible, sometimes you want to think about, like, what scale does it need to be. So r equals 2 is obviously a circle with radius 2. But look at this one, and this is why I left myself more room up here than I did down here, and to me that just makes my graph a little easier to see. What's the biggest value that cosine theta can be? Think about the unit circle. What's the biggest cosine, or sine, sorry. What's the biggest sine ever is? So if the biggest this is 1, then the biggest this r is 5, right? So I know that this is going to go to 5 when this is 1, which is at pi over 2. Oh, thank you. 3, 4, 5. And so that's how I knew I needed a little more space up here, and that just,
if you put some thought into that before you graph it, it just makes your graph a little easier to read, makes your life easier. But just a suggestion. You can always sketch a graph, and if it's, you know, you realize your scale is so far off, you could erase it and then readjust it. Now, to be honest, with this one, so r equals 2 is just a circle where the radius is 2. No matter what theta is, r is 2, so that's easy. This one, when I redid this question yesterday, this one took me a couple minutes to graph. So again, if you want to try to pick up some patterns of what polar graphs looks like, sometimes you can notice some things and take some shortcuts. But short of that, I really, and I'm not going to write out the full table, but I basically just went through and thought, you know, I just did all the stuff where I thought I could do this pretty easily. Like at 0, I get 3 at pi over 6. This is a half, so I get 3 plus 1, which would be 4. So 4 in the pi over 6 directions, kind of hard to estimate. And then I just kind of said, all right, so I started at this angle, I went to this angle, then I did pi over 2, and that was at 5, so I just kind of, I assumed there was curvature to this. And then I did 5 pi over 6, and 5 pi over 6 was over here. And so I assumed those kind of kept going the same way, and then I tried pi, and at pi it was 3, so 3 in the pi direction. And then I basically just kind of kept on going. I did 3 pi over 2 and got 1. And so, and I had 2 other points in here. But basically I plotted enough points to see that it looks something like this. And as much as I've been lecturing y'all about trying to do good graphs, that's a pretty sad graph. But I think it's going to be good enough because this is what I'm trying to find. The area outside of the 3 plus 2 sine theta, but inside of the r equals 2. So what I would say is, on this question, why don't we just start off with all of this area, and that's just a circle, so pi r squared would be 4 pi, but then take away how much of this is not shaded. So if I can figure out this area, the area of this stuff, then I can just subtract that away and be done. So that would be integrate the 1/2 1 of the r squared d theta. And so what I notice here is that these areas I don't want to include are going to be, wait, okay, I lied. I'm sorry, I did not want to do this. I think I tried this and then I changed my mind. If I do all of this, I have to figure out all of this area to take it away, and that ended up being too much work. Excuse me. So instead, I'm sorry, this area could be 1/2 integrate 2 squared d theta. And again, now that I'm really only looking at this half, now I really only want to subtract this stuff that's not supposed to be there. So minus 1/2 integrate r squared d theta. And then now I just really need to find these 2 intersection points, because that's the part of the circle that I want to keep, and it's the angles for this polar curve that I don't want to keep. So I need these same 2 angles. So again, I didn't write my table out over here, and I know the table always seems like it's kind of tedious, but if you do make a habit of making the table and or making points on your graph, then when I found this point earlier and I found this point earlier, I actually already knew those. But this was 7 pi over 6. At 7 pi over 6, sine is -1/2, so you get 3 minus 1, which is 2. That's, oh, well, I guess that doesn't help me. I would need to set these two equal to each other and solve to see that angle. So those should intersect when sine is -1/2, which is 7 pi over 6, and then also over here at 11 pi over 6. They ended up being the same thing. So that is what I integrated, and this question just said write an integral expression. So I don't need to get a number for that. That's enough. I can quit there. Oops. Okay, and I think that should be it. Okay, same thing with number 9. If you would like to try it right now before I go over it in a few minutes, I'll give you a 5-minute head start to see what you come up with. And if you want to save it to when you just get to it, then that's fine also. Did I already show you guys my new stickers?
No.
I did not? Okay, I'll share them with you after this one. You probably won't care about my stickers, but I like them. if you started off and did question 9 and want to see what I did, I'm going over it now. So number 9 certainly needed a picture. So the r equals 5 should be pretty quick for you. And the fact that this is a 5 also means that this is going to need to go about 5 in each direction. Okay, so the circle is easy to deal with, but this one is a little more complicated. So when I made my graph, again, I made the table, plotted some points. Now there is some, this is where I've been saying, if you pick up on some things, it can make the graphing a little bit easier. What does this 2 do to the graph? How many petals? Right, so if you remember that the odd number here gives you that many petals, or if it's an even number here, you get twice that many petals, bless you, then that helps because you don't have to do as much of the graph to figure out what's going on. So I plugged in 0, got 5. I plugged in pi over 6. Now I plugged in pi over 6 and got 2.5. Bless you. I plugged in negative pi over 6 and got negative 2.5. I plugged in pi over 4, got 0. I don't know. You don't have to pick the same angles as me, but I picked some points like that. I found a petal, and because I knew there was 4 petals and they're going to be symmetrical, then I knew here would be 2, 3, and 4. So you can save a bit of time just understanding the petal situation. Okay, so in the end, we were supposed to try to find all of this area. The area inside r equals 5, but outside the other one. So, in this case, what I did is I said, well, that's almost a full circle. So I went ahead and just started with a full circle. And I guess you can do the calculus 1/2 integrate alpha to beta r squared stuff. But if it's just a circle, you might as well just use pi r squared. And so the full thing would be 25 pi. And then if I can subtract the area of the petals, then that would give me my answer. So again, I know that you probably won't be a fan of graphing polar before we're done with it this year. But the tables are, and the making of the graph, you're discovering a lot of the angles you need to deal with. When I figured out pi over 4 was 0 in the pi over 4 direction, I really also figured out that it was 0 in the negative pi over 4 direction. So I could just use negative pi over 4 and positive pi over 4. And then there is one of the 4 petals. And then what can I do to make it be all 4? Right, let's just multiply it by 4. So 4 times 1/2 makes that a 2. And that's not how I did it earlier, but that would be an acceptable way. This should give us, I guess I need to double check it by typing it in. Yeah, that worked. 39.270. Now to be fair, this is one of the things that can also be frustrating about polar. When I did this on my blank piece of paper a couple days ago, I did it a different way. I just didn't do this same thing. I didn't multiply by 4 these petals. I didn't use this petal. I actually just did the whole graph and did 0 to 2 pi. And that was still fine too. So I'm not trying to tell y'all you have to do it my way. I'm just trying to give you a path to get to the correct answer. Okay, I feel like that one wasn't quite as bad, personally, but Okay, there's one more I want to do for a video. It's question 11. So if 11, by the way, I will warn you that question 11, I have seen free response questions that have had stuff like this on here. And number 11 is not a long question, so you might want to try it. But before I forget my stickers, did I miss a day of school a couple weeks ago in this class? Okay, it's B day then. So I had to do a math training day, and they had some stickers out, and most of them are pretty lame, but there was 2 stickers that I liked that I kept. I don't know if y'all can see them very well, but can you see that? What kind of tractor?
A protractor.
Oh.
It's a tractor made out of a protractor. It's a protractor. And then this is a
Calculator.
a cow calculator.
Those are
A
good
calculator.
stickers.
What?
Can I buy one off you?
No. Miss Travis tried to steal them from me yesterday when I showed them to her. Protractor and calculator. Those are very clever. Usually I've heard all the stupid math jokes,
Wait,
but
Mr. Thompson, I made up a joke yesterday. Bowler, I hardly know her. So 11, you were saying?
yes, 11. Eleven's no calculator. And treat 11 like it's a free response question, since I've seen it as a free response question. Which one do you think is more clever, the protractor or the calculator?
I like the protractor.
I bet every time you grab a calculator, though, you're gonna call it calculator in your head.
Do you like the calculator one better?
Yeah, probably. I don't do much with protractors, so.
Yeah.
You better stick with the math. I don't think the stand-up's gonna work.
No, I don't think so.
See, Lane went to the bathroom. He'll never know about it.
I was thinking
Oh, you want to tell him your joke?
no. You won't ever know about the stickers either.
That's what happens when you go to the bathroom. You miss out on stuff.
I'm so much going to the bathroom.
Okay, last one on the board. So 11 gives us a picture of some area stuff, and it's definitely an unusual non-geometry class type shape. Give us a few values in the table, and they ask us to estimate the area, approximate the area, using a right Riemann sum with 4 subintervals. So it's been a while since you've thought about Riemann sums, but if it's 4 subintervals, we need to add up 4 things together to come up with our answer. And now what this is doing is this is saying, like, if I divide this into 1, 2, 3, 4 pieces, I'm not trying to make this accurate at all, but here is where theta is a fourth, a half, 3/4, and 1 at the top. So we could get the area of this piece using that geometry formula that we started with when we started with polar area stuff, the one that we transformed into a calculus equation. So that was 1/2 alpha r squared. R alpha is just it's always been how the angle changes. So for us, when we do integration, the d theta takes care of that, how it changes. So all of these should have a half. And then the angle is how much you're having to change. So from 0 to pi over 4, this angle is pi over 4. From, or I'm sorry, not pi over 4, 1/4. From 1/4 to a half, this angle is another fourth. From a half to 3/4, this is the angle in between those would be another fourth, and the angle in between those is another fourth. So the change in theta, each of those 4 are evenly distributed, but they were all a fourth. They don't have to be equal, but I'm just subtracting, 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 subtracting. And then for r squared, so for this first one, what do you think my r should be if it's supposed to be a right Riemann sum? Not 0. The 0 and 1/4 are the angles. I've already done that. Now I just need r squared. So I should be looking at the r values. So it's either 1 or 3.
3.
How'd you know it was 3?
Because that's the one on the right.
Right, because it's a right Riemann sum. So you want to take the rightmost, so 3, and then this one, this little group, is right here. His rightmost r is 5. Right Riemann sums, you're taking the rightmost values. For this little section, that would be like these values. The rightmost r is 4. And then for this sliver of area, the rightmost r is 2. And then a minute ago when I said treat this as an FRQ, what I was trying to give you a hint on is, unless this is multiple choice and you need to simplify that, just stop there. Just like calculus AB on free responses, you don't have to simplify any arithmetic. If you try to simplify this arithmetic and get it wrong, then you lose that point. If you stop at the arithmetic and circle your answer, as long as it's equivalent to the right answer, then you get the point. So no point in trying to simplify that, but it does come out to be 27/4. Any follow-up to that? Anybody get close to that tried it on their own?
I forgot to do
You forgot how to do what?
right Riemann stuff.
Oh. I thought you would forget the formula, but... Okay, so what I need from you guys, again, all of the questions that we did not talk about together are ones that I made my other BC class do, and I videotaped them yesterday. So there's videos of those.
So try all the rest of the questions, check your answers. If you made a mistake, try to compare your work to the answer guide, see if that's enough. If it's not enough, watch the video. Try to learn from your mistakes. We will have 2 reviews for Polar. So next week on Monday and Wednesday, I've got 2 days of review for you. So that gives you more practice and more time to feel more and more confident about this. And then we'll finally quiz it and move on to some other new stuff.
Yes. Best class I had,